In this video, we're going to be talking about one of our discrete probability distributions called the Poisson distribution. And for the Poisson distribution, we're going to have four different characteristics that we're going to want to talk about. The first is that for the Poisson distribution, the experiment consists of counting the number of times a certain event occurs during a given unit of time or in a given area or volume. So we're counting the number of times an event occurs. Number two is that the probability of an event occurring in a given unit of time, area, or volume is the same for all units. So the probability of an event happening is the same across all units. Number three is that the number of events that occurs in one unit of time, area, or volume is independent of the number that occurs in any other mutually exclusive event. So the probability of an event is independent across all areas. And finally, number four is that the mean or expected number of events in each unit is denoted by the Greek letter lambda. So lambda, which is this upside down looking y, is the mean number of events in a given unit. So now that we have the characteristics of the Poisson random variable, let's look at the actual formulation for that variable. So we have the probability of x number of successes in some given unit of area or volume or whatnot is equal to lambda, which is again our mean number of successes for our particular unit, raised to the number of successes we're looking for, so to the x power, multiplied by e, which is a mathematical constant, raised to the negative lambda, and all that divided by x, which is again our number of successes that we're looking for, factorial. So our x in this instance, so we can have x can be equal to 0, 1, 2, and so on, up to an infinite number of possible successes in a particular unit. So again, just to cover what our different variables are in our formula, we have x is our number of successes, so number of s. We have e is a mathematical constant, which is just equal to 2.71828, and so on. And then we have lambda, which is just the average number of successes in a given unit. And one really nice thing about the Poisson random variable is to calculate the mean and the variance are very simple. Our mean, mu, is just equal to lambda, which you could see by the definition of lambda as the average number of successes in a unit. So the mean has to be equal to lambda. And we also have that the variance, or sigma squared, is also conveniently equal to lambda. So if you're given a Poisson distribution, you need to calculate the mean and the variance. They're just both equal to whatever lambda is equal to. So now that we have the basics for our Poisson random variable, let's look at a quick example. So for our example, we're going to assume that we run a distribution center, and we're looking at the number of orders placed in a given time frame. So we're going to assume that our average number of orders in a given time frame, or lambda, is equal to 10. So for example, we'll say that we average 10 orders for every hour that we're in operation. And we want to see what the probability that x, which is again our number of orders in that given time frame, is equal to 20. So if we average 10 orders, we want to see what the probability is that we get twice that many in one given time frame. So we say what's the probability that x is equal to 20 given lambda is equal to 10. And we know from our formulation that this is equal to lambda to the x. Since lambda is 10, we have 10 to the 20th power multiplied by e to the negative lambda, which is 10, so e to the negative 10th, divided by x, which is 20, so 20 factorial. So we get 10 to the 20th times e to the negative 10th all over 20 factorial is equal to 0.0018. So it looks like the probability of having twice as many orders as average in a given time frame is equal to 0.0018. So it looks like that is very highly unlikely to get exactly 20 orders. However, if we wanted to look at the probability that x is greater than or equal to 20, we would have to do that for all of our different values for 20 and over. So that would be equal to the probability that x is equal to 20 plus the probability that x is equal to 21 plus and so on. So an easier way to do that would be the probability that x is less than 20 and have 1 minus that value. So 1 minus that is equal to the probability that x is greater than or equal to 20. So remember, if we want to calculate the probability that x is within some range, we either need to calculate the probability that x is equal to each value in that range and add them all together, or we can calculate 1 minus the complement of that, and that will be equal to our given value.